Okay, welcome to the second section of Chapter 2, Modeling Distributions of Data. This time we're going to look at density curves and normal distribution. Um, this will be part one of three uh, from this section. So in this one we're going to look at, we're going to estimate the relative locations of mean and median in a density curve. We're going to define what a density curve is, by the way, and then we're going to estimate proportions of values in a normal distribution. This starts on page 103 of your textbook, and it starts out with what exploring a review of Chapter 1 and how we explore data. So in Chapter 1, we developed a kit of graphical and numerical tools for describing distributions. Now we're going to take one more step. So here are the steps for exploring quantitative data. You should always plot your data. You make a graph, a dot plot, stem plot, histogram, whatever, something that's going to give you a visual of what to look at. You're going to look for an overall pattern, the shape, center, and spread. So you're going to describe that. And of course, then you're going to mention any outliers that may have there. And then you're going to calculate numerical summary to briefly describe the center and the spread. So the fourth one we're going to look at is sometimes the overall pattern of a large set of data is so regular that we can actually use a smooth curve. And this is something that is called a density curve. So our first thing we're going to talk about is what is a density curve. So it's a curve that's always on or above the horizontal axis. And it always has an area of exactly 1 underneath it. So we manipulate the units so that we have a unit, an area of 1. The density curve describes the overall pattern of distribution and the area under the curve and above any interval of values on a horizontal axis is the proportion of all observations that fall within that. So, for example, let's look at the example they use in the book. Has to do with the ITBS scores in Gary, Indiana, and that sort of thing. So we have 947 7th graders. I took the vocabulary part of the Iowa Test of Basic Skills. And so these are the results. And so we can, because it shows up as sort of what we often refer to as the bell curve, then we can pretty much use a smooth curve that it basically follows. And so there's lots of data. The main thing is when we have lots of data and they roughly end up like this into some sort of symmetrical, with one peak and, close range like that. So we're going to use this curve. All right, so when we describe a density curves, we're going to use the center and the spread to apply to the density curves as well as the actual observations. The median of a density curve is the point at which we have an equal area on both sides. So the median. So not always does it end up to be a perfect curve, but it most likely does, as we'll look at some examples out of the book. The mean of a density curve is a balance point. So look at the top of page 107, if you will. And we have these 3 graphs, and you can look at where this is showing the mean of the balance point. It's the balance point. And so you can see when we put it on a curve, then it ends up to be exactly balanced because of the weight distribution. The mean and the median are the same if we have a symmetric density curve. They both lie on the center of the curve. The mean of a skewed curve is pulled away from the median, as we learned from from last chapter. Okay, so let's take a look at this idea. So here is a symmetrical, where we have them balanced, exactly the same point, and then here we have where the mean is pulled towards the skewed side. The density curve is an idealized description of a distribution of data. We distinguish between the mean and the standard deviation of the density curve, and the mean and the standard deviation computed from actual observations. So that means we, when we were calculating x bar and standard deviation sx and everything, but now we're going to actually calculate them. We're going to compute them, and so the usual notation for the mean of a density curve, we're going to use the Greek letter mu to indicate that, and then the lower Greek letter sigma to indicate the standard deviation. So that's what density curve is. You can look at page 107 at the bottom to check your understanding, make sure you understand what we are talking about there. Okay, so then it goes into normal distributions. So one particular way, an important class of density curves is a normal distribution or a normal curve. Normal curves are always symmetric. They have single peak. They are bell-shaped. And so we're going to be dealing with these through the rest of the chapter. You should understand that in some cases then we don't get a normal distribution, but whenever the problem or the situation gives us what's called a normal distribution or normal curve, then it's going to be bell-shaped. Could be wide like this one, could be narrow by this one. And so it will indicate the mean with the Greek letter mu, and then the standard deviation there. So one interesting thing about where the standard deviation is if we take a look at, if we start on this curve and we follow along, we can see that it's curving down and curving down and curving down. Well, this point right here where it stops curving down and sort of goes steady for a little bit, that's called the curve, where the curve stops. And so that is the where the standard deviation is. And so we'll learn about that in a bit. And then same thing over here. You can sort of see that's why it ends up over there. A normal distribution is described by the normal density curve. Any particular normal distribution is completely satisfied by two numbers. Its mean and standard deviation. And so jumping down to the bottom there, you can see that we have n standing for the normal distribution, and then in parentheses, looking like an ordered pair, which it technically is an ordered pair because the order makes a difference. We have the mean and the standard deviation there showing those. The mean is always right in the middle because it is symmetric. Standard deviation is called this change of curvature point. And so if we go back to the pictures that we just looked at a second, we can see where the change of curvature happens right there and right there, and then of course it happens again down in here. So we'll look at how that occurs, and is abbreviated in mu sigma. Why are normal distributions so important? Well, because normal distributions are good descriptions of some the distributions of real data. So it's not really great, and it's not for everything, but it's good for some. Normal distributions are good approximations of the results of many kinds of chance outcomes and many statistical inferences that we'll be making in the next chapters occur on the normal distribution. So helps us make inferences. Okay, so something interesting happens on these normal distribution curves, and that is the rule of 68, 95, 99.7. Although there are many normal curves, they all have the same properties. So this rule states that in a normal distribution where the mean is mu and the standard deviation sigma, approximately 68% of all observations fall within one standard deviation of the mean. So we get the 68% happening right there. Approximately 95% fall within two standard deviations. So from this to out to there. So the numbers down here represent the number of standard deviations. That's what it represents. And then approximately 99.7 fall within three standard deviations. So that's why earlier I said that, we don't much go past 4 standard deviations, just because there's not much data in a normal distributed data set. So that's kind of interesting. So now at this time you can take a look at the normal density curve applet. If you go to Schoology, you select the normal density curve applet and complete it. It gives you a feel for how that works and everything. You can pause this video, go do that, and come back, or even possibly do it later. Okay, so let's take a look at an example from page 111 in your book, and it has to do with the ITBS scores. So the distribution for the 7th graders comes out to a normal distribution with a mean of 6.84, a standard deviation of 1.55. First question is, what percent of the scores are less than 3.74? So here we have a plot of a graph of the normal distribution. We have the mean of 6.84, which is right in the center of the curve. So how do you suppose they came up with these other numbers? Well, if you subtract 1.55, subtract one mean from 6.84, you get 5.29. So that represents one standard deviation. If you subtract it again, then you get 2 standard deviations. And then subtract it one more time, you get 2.19. You do the same thing by adding 1.55 to get that. So the scale is produced by putting the mean in the middle and then going up and down by standard deviations. So let's figure out, how would we figure out the score is less than? So we really want the area of that, because if you recall earlier, I said that the area of the bell curve above the axis and underneath the graph, that it is, for normal distribution, is the area is 1. So we just want to know by how much this is. And so one way to do that is that if we subtract 6.84 and 3.74 divided by 1.5, we get 2. Or, as we did earlier, figure out that we are at 2 standard deviations. Well, at 2 standard deviations from the mean, we would have that area, and we have the same thing above. And then from the rule, we know that there's 95% of the 95% occurs in this shaded area because of that rule, because these are 2 standard deviations. So that would leave from 95, the sum of these 2 areas would be 5%, and so we simply just cut that in half, and so we know that the percent of scores less than 3.74 is 2.5%. So we get that. We're able to calculate that because the distribution is normal, and we know what the mean is and what the standard deviation is. let's just jump to an example problem, or the same example problem, and answer the second question. So what percent of the scores are between 5.29 and 9.94? So I supplied you with a different looking normal distribution graph. It's got the rule, the 68, 95, 99.7 in there. But what we want to do is figure out what scores are between 5.29 and 9.94. So we know that there's 95% from here to here, and the 5.29. So let's switch our axes down below. So we have 9.94 here and the 5.25 there. And so we want this axis there. And so we know that we take the 95%, which occurs between here, and we're subtracting out the 68%, which occurs from here to here. And that's about 27%. We then divide that 27% by 2, because remember, we're just figuring out how much is from here to there. And then that's 13.5%. And then we add that to the 95%, or subtract that from 95%. So we're 95% there. We just figured out how much was in this region and then subtracted it off. Yeah. So let's take a look at a different problem on page 129 of your book, number 41. And this is about men's heights. The distribution of heights of men, adult American men, is approximately normal with mean of 69 and standard deviation of 2.5. Draw an accurate sketch of the distribution of men's height. Be sure to label the mean as well as the points 1, 2, and 3 standard deviations away from the mean of the horizontal axis. Okay, so we have this data that we know. We know it's a mean of 69 and 2.5 and a normal distribution, so we can refer to it as this. And then we're going to draw this accurate sketch. So see what you can do about that. Pause the video and see what you can come up with. Okay, so we start with just a regular bell curve and label the center mu. We can go ahead and change that to 69 because that's given in the problem. All right, next we want to figure out what one standard deviation is. So that's going to be at that point where the curve changes. It's approximate. You don't have to be exact when you draw it, but something in that area. We add the 2.5 to 69 and we get 71.5. I'm going to do the other side also. So I subtract 2.5 from 69. So that gives me one standard deviation away. I then go ahead and do the next one. So I add 2.5 to 71.5. That gives me 74. And subtract 2.5 from 66.5. And that gives me 64. And those are my second standard deviation lines. And then a third one is in there also, and 76.5 as well as 61.5. So we're going to be drawing a lot of those, and you don't have to draw them exactly, but you need to get used to how you do that because it's going to show up a lot. Well, on page 129, number 43 has to do with that graph that we just produced. So we're going to use the 68, 95, 99.7 rule to answer some questions about that. First question is between what heights do the middle 95% of the men fall? So we've already calculated that when we did our graph. So that's going to be the 95%. This is the 68, and this is the red ones are the 95%. So it's simply answered as 64 to 74 inches fall within the middle 95% of men. Part B, what percent of the men are taller than 74%? or 74 inches. So we have, we want to figure out what percent that is. Well, once again, I think we've already done this in the last problem, is that, remember we have 95% between the red lines, and so we have 5% on the outside of the red line, so one over there and one over there, so of course that's 2.5%, like we calculated before. And what percent of the men are between 64 and 66.5? So it's going to be that area. What percentage are there? Well, that's going to be that same thing we did before. We have 95, and we subtract out the 68, and then we divide it by 2. And that comes out to 13.5%. Last question is at height of 71%. What's the fourth question? Sorry. The slideshow is falling apart here. 29. A height of 71.5 corresponds to what percent? So, if we have 71.5%, and we want to know what percent is below that, so everything below that. So a couple of ways you could do that is, we know that this is the halfway point. This is the 68%, so we could just we know that half of the 68 would be 34, and so we could just take 50 and 34 and add those together. That gives us 84th percentile. Another way, which is not as clear, is sort of, I don't know, that's kind of what I added. It's 32, 16 above, and 84%. Anyway, that works out probably the best way. I set some problems. That's the end of part 1. And so we're going to go ahead, you can go ahead and work these problems and then go on to part 2 of section 2.2. Any questions, send me an email, ask me in class, and so on. Okay, well, thanks for listening.